Okay, so we'll do chapter 8 review. Magnetism. Okay. Very closely related, of course, to chapter 7. And we started with talking about electricity, and now we're talking about magnetism. Okay, so a few things that we need to remember. First, second, third, right hand rule. Okay, first right hand rule, of course, has to do with a conductor. And what we're saying is for a conductor that if I was to hold my conductor in my right hand, then my magnetic field would be around the conductor, like so, and this will be your I. So the thumb would be pointing in the direction of I, okay? Of current, okay? And your fingers around the conductor in the direction or showing of the magnetic field. Okay, so that was the first right hand rule. Of course, we said that this right hand rule, of course, has a formula. This okay, ILB sine theta, right? And I, of course, is your current. L is your length. B is the magnetic field, and so on and so forth. Okay, so that was ILB sine theta. This was for a conductor. Okay, and then we said that if you have a charged particle, then that's slightly different. So for a charged particle, depending on the particle, if the charged particle is a positive particle, then we use the right hand rule. Correct? If it is a charged particle and it's a negative charged particle, then we use the left hand rule. So positive charged particle, negative charged particle, left hand rule. Okay, my formula for negative charged particles is Fm QVB sine theta. Q, of course, is your charged particle. Cool. V is velocity. B is magnetic field. Okay, so charged particle, if it's a negative charged particle, left hand rule. If it's a positive charged particle and a conductor, right hand rule. Cool? Okay, this is the first right hand rule that we're talking about. Now this force that is created when this charged particle or this conductor goes through an outside magnetic field, which is the third right hand rule. Does that make sense? So that force is only created when that conductor or that charged particle travels through an outside magnetic field. So actually it's the third right hand rule. Okay? All right. Second right hand rule. Second right hand rule is for a solenoid or a coil. Solenoid or a coil, basically, if I was to hold my solenoid in my right hand, my thumb would be in the direction of field, and fingers in direction of current. Okay, this was my second right hand rule. And as I said, my third right hand rule, also known as the motor principle, now this from the video which we saw with Michael Faraday, right? Motor principle. And so what we're saying is, if I have an outside magnetic field, so there is a magnet, there is your magnetic field going from north to south, and if I have either a conductor or a charged particle that is going through this magnetic field, then what will happen is, of course, this charged particle will have a magnetic field as well, and both of the magnetic fields will interact with each other, creating a force which will either push this wire that way or that way, if it comes out of the page or going into the page. And we showed about the right hand rule. Okay, so there is north to south, my fingers pointing from north to south, thumb in the direction of the conductor, and the index finger in the direction of the force. So in this situation, my force is into the page, force into the page. And that force, of course, we said was Fm, which equals to ILB sine theta. Okay, all right, so this was that. Okay, are we good with this? We talked about EE, we talked about FMFC, effects of magnetic field. Okay, so we talked about what happens when charged particles from the sun come in contact with the magnetic field of Earth, how they get caught up in the magnetic field of Earth, start spiraling from the equator downward towards the pole. Okay, and then you end up with the north and southern lights. Okay, so we talked about that. We talked about, okay, let's go to the next thing that we talked about here, which was Ampere's law. Okay, and what we said was, the formula that we did was, if I want to figure out how large the magnetic field is around a conductor or a charged particle, then I would do B equals to K I over R. Okay, K was a constant, proportionality constant. Okay, and I, of course, is your conductor, your current. So this is your current, and R is a radius. And that tells me the magnetic field around this conductor. Or you could write down as B equals to mu naught I over 2 pi R. So both of these formulas will give me the magnetic fields. We said magnetic fields, of course, is measured in Tesla. Measured in Tesla, correct? So this was for a conductor. If I have a solenoid, which is a coil, if I have a solenoid or a coil, then to find out my magnetic field, it's B equals to mu naught N times I divided by L. I is the number of turns. I is current, and L is the length of the coil. Length of the coil. Okay. All right, the last thing that we talked about here was we said if I have two wires, of course without their insulation on it, Okay, I'll have, as I said, a magnetic field around both of my conductors. So imagine if this was north, this was south, this was north, this was south, then you have both of the wires which will attract each other. So there's a force between the two wires when there is a conductor. And what is this force? Well, to calculate this force, we would have said F over L, which equals to mu naught I1 times I2 divided by 2 pi d. Okay, L, of course, is the length of the two wires, two conductors. Force is force. D is the distance between them. And I1 and I2 are your two conductors. Conductors. Okay, so that was force. Now, some people on the test used Fm equals to ILB sine theta to try to give me the force. But this is two wires. I can't just do one. This is just one wire. So we can't do this formula. You had to use this formula when you did the test for Chapter 7 and Chapter 8. Okay? Are we good? Now remember what we said for the last part, which was electromagnetic induction, which is that electricity can only be generated when either the magnetic field is moving or the conductor is moving in the magnetic field. So if you have a conductor and the magnetic field is moving around the conductor, then you will have a generation of electricity, or particles will move. Okay, and or if I have a magnetic field and the conductor is moving. So from the video we saw that you had a magnetic field and the conductor was moving round and round around the conductor, right? That was that force, the third right-hand rule, which kept on moving, which is basically what the motor principle is. Okay, so electromagnetic induction is the opposite of it, where we are causing motion to create, to generate electricity or an electric movement. Okay, so this was Chapter 8. Is there anything that we missed, we didn't cover, we didn't talk about? I'm pretty sure I think I talked about most of it. Most of it was pretty straightforward. Okay, so that's